Next, let's talk about potential energy. Potential energy is the energy associated with the position of an object. If you lift a ball a distance, say y, gravity does negative work on the ball. This work can be recovered as kinetic energy if we let the ball fly. So that means that energy had been stored in the ball, and that storage of energy is called potential energy. So in general, work done by a conservative force equals minus the change in potential energy, which means minus the final potential energy minus the initial potential energy. So the zero of the potential energy is arbitrary. Only the change in the potential energy of the system is relevant. So there are multiple kinds of potential energies. The first one we're going to talk about is elastic potential energy. That is the work done in stretching and compressing a spring, work done in stretching or compressing a spring. And that, by definition, is given by half kx squared, where x is the distance of compression or stretching, and k is the spring constant of the particular spring that you are using. So now let's look at the spring force step by step. The first step is going to be when we compress the spring to the point x equals plus d. The middle point is during its motion when it's at its equilibrium point, and the last one is going to be when it is stretched out. So imagine what is happening here. The distance between the stretching of the spring here and here will give you a positive work done. The stretching from here to here will give you a negative work done, and then the spring bounces back because it wants to go towards its equilibrium point, and that will give you some work done, and then so on and so forth. So spring is going between the points plus d and minus d all the time. And the work done will be plus or minus depending on whether something is moving towards the equilibrium or away from the equilibrium. The other potential energy that we are very aware of is gravitational potential energy. So if you have an object and the only force that is acting on that object is the weight, which is mg, and the force lifts it up from one spot to the other spot, it will gain potential energy when you lift it. And the amount of potential energy that it will gain will depend on the height, because the mass is not going to change, the acceleration due to gravity is not going to change. So the only thing that will give it potential energy is the height that you have moved it to. The more the potential energy stored in your system. So let's look at an example. What is the change in gravitational potential energy of the box if it was placed on a table? The table is 1 meter tall and the mass of the box is 1 kilogram. So this is a very simple example that you can do by yourself. So we are looking for gravitational potential energy, which is mgh. The height of the table is 1 meter and the mass of the box is 1 kilogram. So take a second, quickly plug in the numbers, and come up with answer. I hope everybody got 9.8 joules. The other potential energy that is very important is called the gravitational potential energy, and the gravitational potential energy is between two masses. For example, the gravitational potential energy between the Earth and the Moon, or the Sun and the Earth, or Sun and Jupiter, and so on. In this case, the potential energy is given by G, m1, which is the mass of the first object, m2, which is the mass of the second object, divided by r, which is the distance between the two objects. Note that this gravitational potential energy does not only happen for large objects, but it can also happen for smaller objects, which, for example, a ball that you're holding in your hand versus a ball that you're holding in your hand and you as a system versus the gravitational potential energy of the whole Earth. Now let's look at an example. A planet of mass m has an elliptical orbit around the Sun. The elliptical nature of the orbit means that the distance between the planet and the Sun varies as the planet follows its orbital path. How does the speed of the planet vary as it orbits the Sun once? Take the planet to move in a counterclockwise direction from its initial location. So this is pretty much what it means. So we have a sun, we have an object, we have a certain distance between them, and this is moving in a counterclockwise direction around the sun. So now how do I find the speed of the planet? Well, in this case, I'm going to use some of the information that I have learned. I know that the total energy of this planet and the sun system is going to remain constant, right? So it's moving like this, it's going around and around and around. So what are all the forces that are acting on it? Well, one, it has kinetic energy, right? And that kinetic energy is what is causing this planet to move. And then it also has potential energy, which is gravitational potential energy, right? So that means my kinetic energy for this object is going to be mv squared, and my gravitational potential energy will be g, m of the sun, m of the planet, divided by r squared, which is the distance between r, which is the distance between the planet and the sun. I'm calling it r. What do I know? I know that both of these should be equals to either a constant, or the change of energy should be equals to 0. So in this case, can I put 1/2 mv squared equals g, mass of the sun, mass of the planet, divided by r. What should this mass be, the sun or the planet? Remember, this is kinetic energy of the thing that is moving. In that case, this should be the mass of the planet, this is the velocity of the planet, and so on. So now my question is asking me, what is the velocity of the planet? Well, mass of the planet gets canceled. So what do I have? Velocity of the planet squared equals 2g, mass of the sun, divided by r. And how do I get rid of the square root? I put a square root here and I get rid of the square. So that is my answer. Velocity of the planet depends on the value of g, the mass of the sun, and the radius of the sun. Interestingly, it does not depend on the particular mass of the planet itself. So you could replace, say, Earth here, or Mars here, or Jupiter here, or any other planet that you want, because the only thing that's going to matter is going to be the radius or the distance between the sun and that planet.